physicsinfo.co.uk, another in the series of Physics GCSE tutorials. Topic 14, the particle model of matter. Separate science. Looking at the conventional three states of matter, starting with solids. In solids, the particles are tightly bound, they're very close. They have a regular pattern, they keep their shape. Particles vibrate about a fixed point, and solids are the lowest energy state. In liquids, the particles are still close, but they're less tightly bound. They have a more random arrangement. Liquids can be poured. The particles move past each other, and liquids have more energy than solids. Liquids also take the shape of their container. And in gases, the particles are far apart. There are very few interactions between the particles. They have a very low density. Particles are randomly arranged. They can be held in a closed container. Gases move rapidly in all directions, and they have the highest energy state. We've just mentioned density, and density can be calculated from the formula density equals mass divided by volume. Mass can be measured using a balance, but there are a number of ways to determine volume. In the case of a regularly shaped object, the volume can be determined by measuring the dimensions, height, width, depth. A ruler is okay for this, but a more precise instrument, such as a vernier caliper, will give a more accurate result. All digital instruments should be zero-checked before use, and this balance has a resolution of 0.1 grams. Starting with a brass block of a mass 169 grams. Don't forget to zero check. The steel has a mass of 470 grams, more precisely 470.0 grams. Zero check again. And finally the aluminium, which has a mass of 177.7 grams. The dimensions are measured, and hence the volume calculated, using a vernier caliper. Now this has a resolution of 0.01 millimeters, which is not quite as good as a micrometer, which usually resolves to 0.001 millimeters. Both can be quoted as a way of improving accuracy. These are the dimensions for the steel block. The units used for density, kilograms per meter cubed, and the conversion from grams and millimeters is explained in the core practical video. Now, these are the dimensions for the aluminium block. Correctly, I am measuring the dimension in 3 separate places to get an average for the width of the brass. This is time consuming, but improves the accuracy again. Finally, here are the figures for the brass block. Multiplying these figures will give you the volume in millimeters cubed. Most of these instruments do need turning off at the end. With irregularly shaped objects, the volume can be determined using a measuring cylinder, either by itself or in conjunction with a eureka or a displacement can. Using a measuring cylinder, an irregular object is lowered carefully into the cylinder and the rise in the volume reading noted. You might consider doing the reverse when you remove the object. The measuring cylinder may need to be large to accept the object, and as a result, the scale will be quite difficult to read to any sense of precision. It would be better to use a measuring cylinder with a higher resolution. A displacement can, otherwise known as a eureka can, is filled to overflowing with water and the excess allowed to drip out. Knock off the last drop and place a cylinder with a higher resolution underneath to collect any water displaced. Now gently lower the irregular object into the can and collect all the water displaced. Read off the volume from the measuring cylinder. In this case, 8.4 centimetres cubed. Now weigh the object. The stopper has a mass of 20.4 grams. It is appropriate that both instruments resolve to 0.1 of a unit. As we said before, density can be calculated from mass divided by volume. So in this case, the density of the glass was 2.43 grams per centimetre cubed. The density of a liquid can be found by measuring the mass of a known volume. 1,000 centimetres cubed, or 1 litre, of water has a mass of 1,000 grams, or 1 kilogram, and therefore a density of 1. So back to the changes of state. State changes are physical changes because they can easily be reversed and the original properties recovered. Heating can raise the temperature, but it can also cause a change in state with no increase in temperature. The thermometer stays at 0 for a long time. We call the change from solid to liquid melting, and from liquid to solid freezing or solidifying. Going from liquid to a gas, a higher energy state, we call boiling or evaporation, and from gas to liquid, condensing or condensation. There are some examples of substances that will go from solid directly to gas without going through the liquid phase. This is called sublimation, and going from gas to solid, reverse sublimation. Here's an example of solid iodine crystals being heated. You can see the vapour is soon given off and there is no liquid at the bottom of the beaker. There is ice on the top to give the vapour somewhere to condense, a cooler surface. But when I take the lid off, you can still see the very purple vapour, iodine vapour. A little bit later, and doing the same thing, you can see now that solid crystals of iodine have started to sublime on the lid. And this is later still, where all the iodine vapour has sublimed on the surface of the beaker and on the lid. There is therefore a connection between the states of matter and density. Density is mass divided by volume. The volume of the solid state of a substance is usually the lowest, then the liquid and then the gas. Hence the density of a solid is usually highest, followed by liquid and gas. And of course gas has a very low density indeed. If the density of an object is high compared to the density of water, then the object will sink. But if the density of the object is lower than the density of water, then that object will float. This also applies to other liquids, so petrol will float on water. Specific heat capacity. The specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Let's look at measuring the specific heat capacity of a liquid, in this case water, and a solid, copper. Measuring the specific heat capacity of water is another core practical. Initially, we're going to add 50 centimeters cubed of water to an insulated polystyrene cup. "50 centimeters cubed of water has a mass of 50 grams. Perhaps unusually, we're going to use a lamp as our source of heat, though we already know that lamps produce about 80% heat and 20% light. The electrical energy into the system can be found from the equation electrical energy equals I times V times T, amps times volts times time. Having allowed the temperature to equalize, I have started the stopwatch and recorded the starting temperature. The next part of the video has been edited to make the time pass more quickly. You will note that there is very little change in the readings on the ammeter and the voltmeter as the experiment progresses. There is, though, a steady increase in both temperature and time. And finally, we get to 5 minutes, where we can take a final temperature reading before switching everything off. The formula delta Q equals mc delta theta is given to you, and you simply need to remember that delta Q is change in energy and delta theta change in temperature. The specific heat capacity of water should be about 4,200 joules per kilogram per degree centigrade. The value we calculated was nearer 5,500, but this is partly explained by the energy lost through light, that's about 20%, and the energy lost to the surroundings in heating the air and the table. Exactly the same method can be reused to measure the specific heat capacity of copper. This is a 1 kilogram lump of copper and a 12-volt electric heater instead of the light bulb. We can't use these electric heaters in the insulated cup because they melt the polystyrene. We simply turn on the power, start the stopwatch, and go again for 5 minutes. The equipment was given a little bit of time to heat up first before I started recording. And now the video has been sped up to make time fly. The energy calculation will be simply the reading of the ammeter multiplied by the reading of the voltmeter multiplied by 5 minutes. But 5 minutes is equal to 300 seconds. The calculated units for the energy change, delta Q, will be in joules. After 5 minutes, the final temperature can be noted, and the temperature change, delta theta, can be calculated. We know that the mass of the copper block was 1 kilogram, so we have all the information needed to calculate the specific heat capacity of copper. This value should be about 385 joules per kilogram per degree Celsius. Again, the value calculated from these results is high, but it's not too bad, and it can be explained by the energy lost to the surroundings again. This is the same experiment, a third experiment, with the ammeter, voltmeter and stopwatch replaced by a joule meter. Joule meters measure the energy input directly. Now the experiment is run for a fixed energy input rather than for a fixed time, and this unit only goes up to 9,999, so we'll have to stop it then. Again, the video has been sped up. Once we get to 9,999 joules, we need to record the temperature and again calculate the temperature change. A remarkably similar value for the specific heat capacity of copper is obtained. Now let's look at specific latent heat. The specific latent heat is the amount of heat energy required to change the state of 1 kilogram of substance without a temperature rise. So the energy required to break the bonds when 1 kilogram of water turns into steam, for example. The heater is being used to keep water at a constant temperature. It's been on for a while and the water is settled at 76 degrees. If we zero the balance and start the stopwatch at the same time, we can look to see what mass of water is lost through evaporation as the water is being heated. But we can also measure the amount of energy that causes that mass loss. This time the equation is delta Q equals delta M times L. The change in energy is equal to the change in mass times the specific latent heat. So the latent heat is the change in energy divided by the change in mass. The experiment is run for 4 minutes and the specific latent heat of vaporization calculated. The temperature remained at 76 degrees throughout, and in 4 minutes 1.6 grams of water turned into vapor. The specific latent heat of vaporization of water is 2,260 kilojoules per kilogram. Our figure again is higher, but of the same order of magnitude. Throughout these experiments, heat energy has been lost through conduction, largely with the bench but also with the air, radiation through infrared radiation, and convection, that would be hot air rising. The impact of these unwanted energy transfers can be reduced with the use of insulation. Leslie's cube can be used to demonstrate the impact of different colours or different surfaces on the amount of infrared radiation given off. The tin can is filled with boiling water and the temperature of each surface measured using an infrared thermometer. Black is a very good absorber and emitter of infrared radiation, heat. Silver is a poor emitter of heat and therefore a good insulator. And this is the principle behind the thermos flask, more properly called a Dewar flask or a vacuum flask. Silver reduces heat loss by radiation and the bung heat loss by convection. Finally, there is an air gap between the layers which reduce heat loss through conduction. Unlike liquids and solids, due to the large gaps between the particles, gases are easily compressed. If you squeeze or compress a gas, the volume decreases and the pressure increases. These ball bearings in the syringe represent a solid, and you can see that you just can't push the plunger down. And this is also true with the liquid. Whilst in comparison, the gas is very easy to compress. Pressure is the result of collisions between gas particles and a surface. The flight of these particles can be resolved into two components, and there is always a net force acting at right angles to the surface. This arrow represents one particle colliding with the wall of a container. The particle bounces off the wall, it is reflected. This flight path can be resolved into two vectors, one parallel to the wall and one perpendicular to the wall. It is this perpendicular line that represents the net force which acts at 90 degrees. As we've said, pressure is the result of collisions between gas particles and the surface. The rate of these collisions will increase if the volume of the container is reduced, or if the temperature and hence the kinetic energy of the particles is increased. The model shows that if you halve the volume, you effectively double the pressure. There are twice as many collisions with the outside. So back to the start. If the temperature is increased, the kinetic energy of the particles also increases. The particles move faster, and therefore there are either more collisions with the wall or the collisions have more energy. For a fixed mass of gas at a constant temperature, there is a relationship between pressure and volume given by the formula P1 times V1 equals P2 times V2. You should expect simple substitution calculations, but the formula will be given to you. Here's an experiment where the volume of a gas can be compressed using a piston driven by a screw thread. It's possible to change the volume, take readings of the pressure, and then plot a graph of the results. This video clip has been sped up. You can pause the video, take readings of volume and pressure, and use the data to plot a graph. This would be a suggested practical. And finally, with a bicycle pump, as you push down on the handle, you're doing work. The cylinder of gas is compressed and the pressure increases. The work that's done increases the kinetic energy of the gas, and hence the temperature rises. That's it. Thank you for watching.